Good afternoon and welcome to today's machine design webinar. This webinar is titled Long Fiber Composites, High Performance Materials and Design, sponsored by Plasticomp. I'm Jeff Kearns, Technology Editor with Machine Design. Let me explain how you can help participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. We welcome your question during today's event. Just type your question into the question window on the side of your screen, then hit the submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. Please also be aware that today's session is being recorded and will be available on the Machine Design website within the week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now let me introduce today's speakers. Eric Wallen is Vice President of Technology at Plasticomp. He manages teams responsible for composite material development and application design involving the firm's LFT products and services. Eric has over a decade of experience working exclusively on long fiber reinforced composites and is a graduate of Winona State University, where he earned a bachelor's degree in composite materials engineering. Mark Henry Walken is product development engineer with Plasticomp and leads the company's product design and performance analysis team. Mark Henry earned a master's degree in mechanical engineering with a certification in plastic product design from the University of Massachusetts. He is also a Six Sigma Black Belt certified. Now let me turn things over to our presenter. Eric, the floor is yours.
Okay, thanks Jeff for the introduction. And thanks to all those sitting in for taking time out of your day to be part of the webinar. Today's discussion will be two-part. The first portion of the discussion I'll be covering, and we will be touching on basically long fiber 101. What is long fiber, and how does it differ from short fiber or unfilled compounds, and what are the performance benefits of using long fiber materials? We'll move on to a couple of the more typical fillers or fibers that are used in our materials, long glass and long carbon fibers, and compare and contrast the characteristics there. And then I'll wrap up my portion by talking about some of Plasticomp's unique formulations. The second portion of the webinar will be covered by Mark Henry, and he'll be touching on design strategies using our long fiber materials, as well as tips to maximize part performance using LFT, and how we use simulation tools to help in that process. So let's just talk about fiber reinforcement in general. Short fiber and long fiber are both very cost-effective methods of increasing the mechanical properties of lower-cost thermoplastic polymers. You'll see a significant boost in performance by filling with short glass or long fiber materials. However, there are some advantages of long fiber that give you mechanical boosts that short fiber cannot give, and we'll cover those in a few of the upcoming slides. Fiber reinforcement can be incorporated into any thermoplastic polymer. However, it tends to give a bigger boost in performance when used in concurrence with semi-crystalline polymers. The structural capabilities will be picked up when using higher engineering type polymers such as nylon, but polypropylene is a very common material for reinforcement. Now we will focus solely on long fiber today, and we're going to cover some of the differences from short fiber materials. And one of the main differences is that the manufacturing process gives us the ability to maintain longer fiber from the start. So if we look at how long fiber materials are processed, we start with a continuous tow of fiber. We're dragging that fiber through a melt impregnation area, and that is our die, where materials are melted at high temperature and the long fiber material is pulled through and exits the other end of the die, where we have very specifically sized orifices. We can typically manufacture material that will go from 20% in fiber content by weight all the way up to 60% by weight. In some cases 70%. It's by weight. It's dependent on the fiber type and the polymer we're working with. And that is controlled by the size of the exit orifice. Once the material exits, it's cooled and then chopped, and the resulting pellet length is typically 12 millimeters. However, that can be chopped to different lengths if necessary. If you compare that against how a short fiber material is processed, short fiber will start with chopped reinforcement that is already typically less than 12 millimeters in length. It is then added into an extruder where it's combined with the polymer of choice, and by the time it exits and is formed into a pellet, the length of the fiber is typically lower than 1 millimeter. Now why that's important we'll touch on in the upcoming slides, but with long fiber, because you start with a continuous strand, you are left with unidirectional reinforcement that is as long as the pellet you've chopped. And if molded properly, you can maintain a fiber length in the finished part that's up to 3 to 4 millimeters on average. Where by the time you get done molding a short fiber material, you're typically less than 1 millimeter in length. And again, we're going to touch on why that's important shortly. So why long fiber? The main benefit that you'll get from long fiber is a large increase in impact resistance, especially when compared against short glass. With both short glass and long fiber, by just inputting that fiber, you're going to get a increase in modulus. So that's more a function of the filler content. And the higher you can go in filler content, the stiffer the material will be. That's one advantage that long fiber has, is because of our processing methods, we're able to go into reinforcement levels that are higher than what you could typically achieve with a short glass product or a short fiber product. So that gives us the ability to increase stiffness even further. When you look at unreinforced materials, adding any type of reinforcement, whether short or long, is going to raise your heat deflection temperature. So both can do the same in that regard. With strength, that is also more a function of content. However, fiber length will play a part there, and we have a slide coming up that's going to demonstrate that. Again, the advantage with the long fiber is that you can step this up to high levels. However, there is a point where you start to level off on strength as you add more and more filler. And as I mentioned, where long fiber earns its stripes is with the impact resistance. So the longer you can keep your fiber length in the final part, the higher your toughness will become. And what's interesting with long fiber materials is your impact resistance is the same at room temperature as -40, and to certain high temperature levels as well. So this slide does a better job of demonstrating what I was trying to verbalize. If you look at the screenshot, you'll see that fiber length is along the bottom axis, and on the y-axis you have the different performance levels. And it's noted here that this is in polypropylene. However, the same is true in most semi-crystalline polymers as far as performance is concerned. So again, fiber length doesn't play a big part on stiffness, but you can see that as you start to extend out into the 1 millimeter length and higher, you do get somewhat of a strength increase. Toughness, as you push out into the 4, 5, and 6 millimeter length, starts to become an exponential increase. And again, that's where long fiber, if processed correctly, can give you an added benefit. You'll get that stiffness, but you're going to get that added durability that short fiber just can't give you, especially at low temperature. We like to show this slide to prospective customers for several reasons. It gives you the insight into how long fiber works. If you can maintain that fiber length, as I've mentioned, you'll get a lot of fiber entanglement, and it creates a skeletal structure that gives you the performance that we've been touching on. One of the pushbacks we'll get, or concerns from people, is that, well, that long fiber isn't going to be able to fill real detailed areas. And we use this slide to kind of show that we can indeed fill areas, and we've got some bolts and nuts that have also been produced out of our material that, when burned off, fill into the very detailed areas of that nut, the threads and everything. So when we look at the benefits of long fiber over short fiber in particular, one of the benefits with that impact strength is that you're able to thin out the walls. So if you've got of a certain component, so if you've got a short glass part and the walls are thick and you're looking to reduce the thickness to lightweight that material, long fiber may be the answer because of that increased impact strength you'll get, especially in thin-walled parts. Some other advantages that long fiber have over short fiber is that you're going to get higher fatigue endurance, better creep resistance, and you get a very low coefficient of thermal expansion. And depending on the materials you're using, they are comparable to metals. Now, where long fiber really earns its stripes is in metal substitution. And I think it's important to mention right off the bat that you can't just look at a component as it is in its metal form and just take the cost per pound of a long fiber material and substitute it in and do your analysis. More often than not, once you look at a metal part and convert that to a composite part, it's going to change its shape and its design, and Mark Henry will cover that in his portion of the presentation. But it is really evaluating an entire system cost, not just a cost per pound. And I know that's an immediate rejection point when we talk to some companies, but once we've discussed with them the advantages of converting to a composite part that can be injection molded and discuss that we can eliminate secondary operations, we can consolidate parts, there is no need for welding or stamping anymore. If you're painting, we could potentially eliminate the painting process by putting different surface coatings on the tool, which will then transfer to the part. We can pre-color materials so that you can avoid painting with the pre-colored compounds. And then in the case of trimming with some cast materials, we can produce a net shape so the trimming operations could be eliminated. And the real advantage of injection molding is the speed that a part can be produced. And so you can get very repeatable parts in a very short amount of time once the tooling has been developed. Typically cycle times for parts are 2 minutes or less. So again, very repeatable, predictable parts in a very short time frame. And I think other people are afraid of the conversion process because they don't think that composites lend themselves to complex geometries. But because we're able to use thin walls and have the strength that we have in our materials, we can get into very complex shapes. And again, because you're using an injection molding process, you're going to get very repeatable parts. Usually we just need to understand, we try to get involved early on in the process so that we can understand all the inputs and understand what the target cost is. If we have the proper inputs through our use of CAE tools such as finite element analysis and also mold flow analysis, we can work with the partner to convert the part from metal to composite so that it meets all the performance and price goals. And we'll typically look at this holistically. We'll recommend a material that works with the design so that we get the most positive outcome. I should mention too, with just some of the attributes, that corrosion resistance is another big one for our materials. We can work in very caustic environments and substitute for stainless steel, for example, where stainless steel has only been the option. And another interesting one is the radiolucency of our materials, that we have radiolucent product, which means it's invisible to X-ray. So where that's important especially is in a trauma center. If a medical device was attached to a person who had had some traumatic event and the doctor needs to take a look for an X-ray, typical metal components are going to show up on the X-ray, and that's what this photo to the right is showing. Is on the bottom you'll see the metal component, and so the doctor will not see through potentially to the patient injury. On the top is our composite component, and as you can see, it's shadowed, but you can still see through and to the bone and to the potential injury. The only components that are still showing up there are the metal inserts. Now, I kind of skipped ahead and talked about this slide already, so again, just to reiterate that when we're doing a conversion, we'll usually want to talk to the customers up front and get the proper inputs so that we can have the most desirable outcome. So now we're going to move on and just cover the different reinforcements, or the most typical reinforcements that we'd use in our thermoplastics. And the most common that I think everyone's familiar with is long glass fiber. Long glass has been used in the industry for many, many years, and it's a very economical filler. Very low cost, does a very good job of improving the overall mechanical performance of a part. And the advantage that long glass has over, or just glass filler has over carbon, is that it can be colored. So, you know, if you look at what are the big ones, you get a performance boost when added to an unfilled polymer at a pretty low cost, fairly affordable. You get a part that's impact resistant, and it's, as I said, affordable. However, you cannot get that performance, and it doesn't quite have the density that a carbon fiber product would have. Now this slide just shows a spider diagram of several materials that are compared to each other. And as in the center is the unfilled product, and you can see the properties there are quite low in comparison to even the short glass product, which is labeled as SGF. And then we have two products that we're highlighting here. The first is our standard long glass fiber product, and then we also have what's called a maximum toughness grade, which is the MT product. And where that really stands out is in its impact performance, and we'll touch on that a little bit later in the presentation. But you can see the nice balance of properties you get with the long fiber materials compared to short glass. This really spells that out. And here's just another look at some data. If you look at the columns on the left, I think it's important to note that it's not just about the fiber itself. The polymer does play a big part in this. So if you move beyond polypropylene and into some of more of the engineering polymers and the exotic polymers, you're going to see that the strengths and stiffness will pick up. So again, there's a cost by moving to those materials, but we like to work with the customers to tailor a product that fits their needs. So, you know, we can look at the price and performance benefits of each product and pick the right one that suits the customer. Now on the right hand side in those graphs, we're just comparing short glass against some of our long glass materials, and you can see where on the right hand of those that first chart we have our impact. You can see that long fiber definitely wins out in that regard. On the bottom, similar slide comparing some different materials to magnesium and aluminum. So again, a clear winner there with the long fiber materials. Now I mentioned earlier the nuts and bolts that are produced using our material. There's a shot of those, and when we burn those off, those threads are filled out with our fibers. So again, the misnomer that our materials are not going to fill out real intricate areas is false. We've got the medical clamps that I mentioned that had the radiolucency, as well as a very durable part that's very demanding application, and that's where some of our maximum toughness formulas come into play with the boat prop. You can imagine the abuse that this type of a product would take, and that's where our maximum toughness grades come in. So now we're going to just touch on long carbon fiber. And I think the first thing that comes to mind when we mention carbon fiber or carbon fiber composites is performance. Everybody thinks about that you've got very high performance with carbon-filled materials. And when performance is of the utmost importance, carbon fiber will win out hands down. The density compared to glass is lower. And when you use a carbon fiber reinforced material, you can get a product, when designed properly, that's 50% lighter than an aluminum part. Now at the bottom, you can see that we're comparing some specific strength against the density of a material. And again, you can see where carbon fiber has its value when compared against glass fiber material. Now, carbon fiber is adopted widely in performance areas, performance markets such as aerospace, defense, and sports and recreation, where performance is king. That high-tech perception will only go so far. The big penalty is that the price is quite high, and that is a big entry barrier, especially in high-volume type markets. For best performance, we usually look at 20 to 40% by weight filler content. Higher loading percentages start to taper off in strength and don't give you much beyond a increase in modulus, but processing does become quite difficult. Performance data here, you can see a similar story with the polymer also being a key contributor here in the mechanical properties. Part of the reason you're seeing the drop in the polypropylene versus the nylon is that the polypropylene does not bond well to some of the existing fibers, carbon fibers that are available. So you're seeing a big decrease in strength characteristics, where the bonding is a little bit better between the glass and the, between the carbon and the polymer. So you get a better transfer of properties from the matrix to the fiber themselves. When looking at the right again and comparing some different properties, you're seeing the differences and the advantages of the long carbon fiber compared to short carbon fiber, and of course unfilled material. And similar in the bottom slide, we're throwing the magnesium and the aluminum in there when looking at specific strength of some of our materials. Now, as we look at some of the applications that carbon fiber is used in, you can see we've moved into the performance arenas, and every one of these industries is quite interested in the lightweighting advantages that carbon fiber gives you, along with that stiffness. I want to touch on plastic comp and some of our unique formulations, and maybe the unique way that we like to partner with customers. Although we do have typical off-the-shelf type products, we tend to want to work with customers and partner with a customer to develop a product that's right for them. So we can give you a product if you call and say, I just want something off the shelf. We can certainly deliver that. However, we prefer to talk to you in more detail, understand what needs you have with your part performance, and then recommend and develop a product that specifically fits your needs. Another advantage we have is that we do have these in-house design and analysis capabilities, so we can very quickly come up with concepts for you when converting from metal to a composite part. We also do have some in-house molding capabilities so that we can quickly produce a part for you to look at and test. So our niche really is to not attack existing space. We don't want to go and try to win out on an existing long fiber application. We're really about finding new space and new markets and finding partners that we can work with to convert from metal to composite. That's really where we have the most fun. So it's new applications. We'd love to work with different customers, understand their needs, and then give them solutions. And that's really how all our materials have been developed, and I'm going to touch on a few of those in the upcoming slides. So the first one is hybrid material, and this was really was developed because as we heard more and more automotive companies discussing the need to move to lightweight carbon fiber composites because of the fuel economy regulations, we knew that everything was going to be moving to a carbon fiber based product. However, the big drawback was the cost of the carbon fiber. So our idea was to develop a hybrid which brings in the less expensive glass with the carbon fiber to try to find a point on the price and performance curve that was more attractive to automotive customers. And so we have the ability to tailor the ratios of the carbon fiber with the glass, again, to find the right cost point and the right performance point to hopefully meet their needs. Now this could be adopted to other industries as well, and has had a pretty good reception in different market spaces. Now this chart shows the differences between the hybrid materials and some of our more typical carbon fiber material. If you look at the 40% product, all carbon, you're going to get some advantages in stiffness and strength. But the glass carbon hybrid does push out and fill in the gap, pushes out beyond what a glass-only product could do, and gets very close to the performance levels of a 40% carbon product, but the cost is significantly reduced. So that's the advantage. And as always, there's trade-offs. If it's impact performance only you're looking for, then an all-glass product is probably the right choice. If it's stiffness and price is not as important, then of course the carbon fiber only is probably the right choice. However, if you need a balance, then that's where these hybrid products could come in. Now another product that we've had some very good success with is the maximum toughness grade. And I think I mentioned earlier that in thin-walled applications, this is where this product really shines. You can get a notched impact increase that's 40% higher than our standard LFT products, and 400% increase over some of the short fiber compounds. So again, when impact strength is of the utmost importance, this would be the material to choose. And here is a chart that shows the comparisons between unfilled, some short fiber products on the left, all the way through our standard products and into our maximum toughness grades. And as you can see, there's a very significant jump there in impact strengths. Another development that we've had is a product that we call Velocity. And what this grade gives you is higher flow, better aesthetics at lower temperatures. One knock on long fiber materials, and especially high loading long fiber materials, is that at times you can get surfaces that are not as desirable as you'd see in a lower fill content. So with the Velocity grade, this will give you the ability to have a better looking surface at these higher filler contents, and also if you're having difficulty filling a thin-walled part, this material may be the answer. I've also noticed in certain cases where molders were able to reduce the temperatures that they were processing at, which helped improve cycle time while maintaining part aesthetics. This product is a transparent, contact transparent, translucent material that is structural. So we were able to load this material up with glass fiber from 20% to 50% by weight, and still maintain some contact transparency. So you've got a structural component here that would give you the ability to see through if you had any types of revealing internal components that may need maintenance from time to time. So it gives you the ability to have a monitoring window that has some structural integrity. And I think I should mention as well that it's not just polymer and fiber. We do have the ability to also incorporate other additives to give our materials other attributes. So if wear resistance is important, we have special additives that can be introduced to the compounds to give you higher wear resistance, flame retardancy. And on the appearance side, I mentioned that we are able to customize the color that of the product when it's glass fiber. As you can see on the right, those are some actual pellets that we have in-house that we've pre-colored. I think it's important to note that we will incorporate the color right into the actual pellets, and that'll help get a more consistent part as far as color is concerned from shot to shot, as opposed to adding the color in separately at the press. So in review of what was covered in the first portion of the presentation, long fiber is the most economical method of increasing mechanical properties, and especially the impact strength. When looking at overall performance, the long carbon fiber material would be the best solution. And as I just most recently mentioned, if you're looking for the best balance of performance and price, the hybrid product would bridge that gap. And with that, I'll turn it over to Mark Henry.
Thank you, Eric. Okay, so typically the situation with fiber reinforcement is that people are nervous about using it. And that's because their designers haven't dealt with it before. So let me give you a few tips that will make you feel a little bit better about using it, know what to keep in mind while designing with it. And then that way you'll feel more comfortable using the material overall and find its benefits. That'll help you out. Okay, so the three things that you want to keep in mind when designing a fiber reinforced part is the injection molding process, the long fiber material itself, the part and tool design. All three of those are key. When it comes to the injection molding process, you want to make sure that you're using the right screw that isn't breaking down the fiber in the barrel. When it comes to long fiber material, you want to pick the right resin in combination to those fibers. And what kind of fiber? You can have glass reinforced, you can have hybrid, and you can have carbon. So those are things to keep in mind from the get-go when you're starting to design your part. All right, another way of viewing that is you want to think about your fiber content on top of that. We typically range from 20% to 50% fiber content. 20% will give you more strength than your virgin resin. And you really don't want to go above 50% typically because you start seeing a diminishing return on your strengths after that. It's also important to note that you're going to get a higher stiffness with the more fiber content that you have in the part. Once again, that molding process, you want to keep that in mind. Make sure you're not breaking down these fibers as they're going into your part. You want to look at your fiber chemistry and fiber morphology, because this is where we can start tailoring the resin and the fiber to your needs. Depending what kind of surface you want to see, how easily it needs to flow through your part to avoid short shots, and just how stiff it needs to be also. You want to look at your fiber orientation, because a simple way to think of that is when you have a rope. You need to align your force in the pull direction. If you pushed a rope together, it won't take any strength. So that's the kind of mindset you want to have when you're designing for a part. Make sure your fiber is oriented to your load so you can optimize on its strength. You also want to look at your fiber length. Does it need to be long fiber? Can it be short fiber? How much fiber breakdown are you dealing with? Those are all things you want to keep in mind. All right, on this slide I have some examples of what to think of when you're dealing with these parts and where it can be useful to you. On the top left, we have a crossbow riser. This needs to be light and it needs to be strong. There's about 800 pounds of load that's placed on this part. But at the same time, you want it to be light because now this is being held by a person. It's being carried around. You don't want to lose energy when you're walking a couple miles in the woods. Towards the bottom, we have an airline seat component. And this is a good example of the molded-in intricacy that you can get, where you can place material where you need it to satisfy strength requirements, and not have material where you don't need it, so you can reduce weight. And machining a pattern like that is just going to add costs. You don't want to deal with that. You'd rather machine it into the mold the first time, and have it in each part consecutively afterwards, without adding any cost. On the right side, we have a part that worked as a cell phone bracket. The goal of this part was to be really thin so it can fit in the cell phone, but at the same time hold all the components rigidly so that they're not bending or having any flex. This was also nice because it needed some EMI shielding, which was aided by our carbon fiber in the part. Okay, so another few attributes that are nice when it comes to metal replacement is that this retains geometric dimensional stability under loading. More easily said, it's quite stiff, especially when you're dealing with carbon fiber. Glass fiber is also much stiffer than virgin resin also. And the fiber also helps to resist against surface damage, and that's because the fibers are going right up to the surface. So when you scrape the part, you're still having fibers holding whatever details as in texturing on the surface. Another huge benefit is that these materials are about 50% lighter than aluminum, which is a big deal because if you're using aluminum, it's probably because you're already weight conscious on the part as it is. You also have that molded-in geometric intricacy that we talked about. If you want to add ribbing or supports or fillets or any of those kind of details that you know are going to add expense on machining, you can do it on a plastic injection molded part without adding any cost. And it also gives you design freedom aesthetically. If you want to have a pattern on it, a texture on it, where machining it just isn't an option, it's nice to go to molding for that benefit. Also, you have the injection molded cycle times. Typically about a minute if it's a thick part that you'll see. It can get up to 2 minutes, but that's still much faster than 3D printing, machining, casting, and that really helps bring down the cost because you can just make thousands of parts very quickly. You have assembly part consolidation. That helps with reducing your labor costs, and I'll get into that on future slides. And then you have electrical conductivity manipulation. I mentioned before that carbon fiber has EMI shielding. It has a low level of it, which is very useful in a lot of parts, especially now that electromagnetic emissions are needed to be reduced on a lot of parts, especially in military or anywhere that you're dealing with a lot of electronics in a small location. You don't want them interfering together. And then it also goes to glass parts. Glass-filled parts are electrically insulative, which also comes in handy. We see a lot of people asking about bolts, and just because they don't want to conduct any electricity through those bolts, and there's different parts like that. Then you have lower thermal conductivity. If a person's touching it, or if another component's touching whatever your design is and you don't want it to melt or you don't want to burn a person, this comes in handy there. In molded colorability, when you're dealing with glass fiber, you don't have to paint the part if you can get the color matching to be what you want it to be, reducing any paint cycle times or costs having to do with that. And then this material's corrosion resistance too. With metals, you're going to have to be worried about rust, and you don't have to deal with that in a plastic component. I wanted to cover a few threading techniques that we have. This is important in machine design. When it comes to this material, it's stiff enough that you can actually machine into it, and that's good if you want to get some direct threading and you don't want to have to deal with inserts. And the pull-out strengths were quite a bit. Even for glass fiber reinforced materials, we are seeing it ranging from 1,000 to 2,000 pounds of pull-out strength. You also can sonic weld in inserts if you feel more comfortable with that, or if there's a compression load that you're nervous about. So this material lends itself to both direct tapping and sonic welding in inserts. Along those lines, I also want to bring up that you can insert mold around any kind of insert you're interested in. Depending on the mold design, if you can hold that part in place, you can mold around it, insert those parts into the mold directly, and then they'll be one piece with your molded part. That comes in handy in a lot of places. Let's say if you have wear surfaces that you're concerned about. That can really help. Alright, that also leads me into part consolidation. When you're dealing with metal parts, many times you're going to make each little piece, machine it out, and then you're going to bring it all together, and then you're going to need assembly strategies like screws, adhesives, anything like that, and that involves tools and technicians for each little step. So you can reduce your labor costs by bringing these all in as one piece. So the image on the bottom, each dot represents a different part that was able to be consolidated into the one unit that is there in the image. This also reduces your assembly mistakes, human error, That helps a lot too, and you can reduce that production time that it takes because you have that whole step of assembling these parts and adding any bolts and bearings or anything like that you can just consolidate into one part. And let's move on. Alright, another thing that's worth noting is fiber reinforced parts are much less susceptible to shrink. That being said, you can actually have thicker parts. That gives you a lot of design freedom. A typical range that we think is helpful is about 60 thousandths to 500 thousandths of an inch. Now that's going from our thinnest to the thickest pieces that we would recommend. I wouldn't go anything less than the 60th hour. Then you're going to start having trouble with higher fiber loadings flowing through your part. And at the same time, anything above 500 thousandths, your fiber orientation is much weaker because there's tumbling taking place. So that's why we recommend a thinner part. Ideally, we would recommend an 1/8 inch. That's what our test bars are. Those are ASTM standards. We find a lot of strength there, and it starts slightly diminishing as you increase. From our findings, we're seeing that 200 thousandths is still a good thickness. You still have great fiber orientation there, and you still retain almost all of your strength. I wouldn't range higher than the 400 thousandths, personally, from what I've seen. When you're at 400 thousandths, you still have that fiber strength, you still have good orientation, but it is quite a bit diminished from the 200 thousandths. So when people ask about creep, let's say, we say try to keep your loading under half the max load that you're going to deal with, just to reduce what you're dealing with creep also. And then also we want to say keep in mind your fiber orientation, as I stated earlier. That's a big deal. If you're getting a lot of tumbling in your part because you decided to make it too thick, you're going to have diminished strength in the part. Okay, along the lines of thickness, this slide kind of illustrates it. This was a connecting rod that we were looking at about a year ago. Now it started out quite thick. It was over 1 inch thick, and here, I better explain what those dot colors mean to make this a little bit easier. The green dots are excellent fiber orientation, while the orange dots show that your orientation is decreasing. And the red dots mean you have poor fiber orientation, so you're not maximizing on your strength on the red dots. So now, to look back at this connector rod with that in mind, you can see that the thick part had excellent fiber orientation towards the walls, but as you started to go to the center, you quickly realize that the fibers start tumbling, and a majority of the thickness of your part isn't utilizing your fiber strength as much as it could be. On the image right next to that, we added ribbing, which we didn't really add ribbing, we kind of cored out the part, but it looks like ribs. Now this helps with your fiber orientation drastically. You can see that there's a lot more green dots, meaning you're having excellent fiber orientation in those locations. And each rib is over 200 thousandths thick, and you're still getting that fiber orientation. And then towards the center, you see a smaller localized area where you have poor fiber orientation. So because you're getting more fiber orientation in this part, it was actually able to take 200 pounds more strength than the part on the left. Near the bottom, you can start seeing just an isometric view of those parts. What I did to get those break shapes is I notched both parts in the middle, and then I impacted them from above. And these are the consequential breaks that you're seeing here. So on the left part, you're seeing where the fiber tumbled. It was a straight break. It broke right down. And on the right part, you see that it's more of an ugly break, where it's much more jagged. And, you know, the jagged break, the uglier break, is actually ironically the better break, because it has to rip through more interfacial area to reach that break, which means it took a lot more force to get it there. And on the very bottom, you see an image of, this is a primed part, where originally in the mold there was a virgin resin in it, and we were priming in, adding fiber and pumping it through afterwards. So this is kind of a rare occurrence where you get a chance to see the 7-micron wide fibers filling a part. It kind of gives you a different point of view of just how fine these fibers are as they slide through. I always thought that was interesting. Okay, there's a familiar part. Eric went over it. I'm going to go over it from a designing point of view. Right on that surface, you see this multi-directional fiber layout. This network of fibers really helps you with your impact loads, which is what really helps long fiber resist impact better than short fiber does. So what really helps there is that you can't 3D print that geometry. That's why I'm not too nervous about 3D printing, because you're just not going to get that fiber network there. So you're better off injection molding the part so you can get that network, that impact resistance. Right under that, you see an image of a fiber break section. And this is where you can start seeing a residue on those fibers. And that residue is a good thing. That means that it actually bonded to the resin matrix around it, which added resistance to the break. It actually had to pull out all of that extra bonded area from the other side. The image below that is kind of a stress diagram of how each fiber is gripping the matrix around it, just to give you an idea that there is a surface bonding relationship to that matrix. So on that part, I also want to point out that the bosses are thicker than normally recommended to typical plastic design standards. And normally that's frowned upon because you're going to get a lot of shrink and a lot of warp, but this is where fiber filling your part really helps you out. Because it doesn't have as much shrink, you're not going to have that issue there, and you can feel free to have a thicker boss. You also see that molded in intricacy that Eric spoke about earlier. We can still fill those fine sections with long fiber. Okay, I want to cover gating and runners. So one of the challenges that you're going to have when you're using any kind of fiber reinforced material is that you can't have those 1.5 by 1.5 millimeter gates anymore. That starts actually breaking down your fiber. You can still use it, but your shear forces are going to be much higher. You're not going to get quite as much out of your fiber strength when you do that. We recommend some wider gates that typically you're going to want to machine them off or clip them off. That's the downside. But you enhance your fiber length in your part drastically. We also recommend, as you see on the right, more rounder gates and rounder runners. We find that that really reduces your pressure also. Towards the bottom, this is an injection molded test bar set for flex and impacting and tensile testing. You can see here we use lofting and sweeping runner systems. You want to avoid sharp corners in these runner systems. That way you also avoid breaking down your fibers more. Fan gates are very useful for aligning your fibers in the tensile direction also. Let's move on. Okay, another point along those lines is auto degating gets a little bit trickier when you have these wider gates. Now these long fibers are quite strong, which in this situation makes things a little bit tricky. If you auto degate, you could get fiber rip out from your part. As long as it's not in a cosmetic area, that's not really a concern, but if it is in a cosmetic area, you have to think about that. Okay, now to cover how we help clients, because they come to us asking, okay, how do we optimize for this material? We feel more comfortable with you doing it. Maybe you're more comfortable with aluminum and you never had to worry about moldability or weld lines before. We can walk you through that process too and help you out to make that transition a little bit easier. So on the top is that example of that crossbow riser. What we want to look at is a mold flow. We'll run a mold flow simulation, see how fiber is flowing through your part, where your weld lines are, and we also want to run an FEA. We want to find out where the highest stress parts are, the sections of your part, I mean. You want to make sure you don't have any weld lines in those high stressed areas, and in fact you want to have a better fiber orientation there. So it's really a triple play between your design, your moldability, and your stress analysis, which we'll walk you through. We typically make a PowerPoint to help explain what's happening in your part. And that's really going to help you out, and just to walk you through how everything works from a moldability perspective and a long fiber perspective. And then after we find these things out, we redesign to fight that, to fight those stresses, and add material where you need it while removing material where you don't. So you can end up with even more than 50% weight reduction. That'll keep you able to compete with your field entirely, just to give you an edge over your competitors. So along those lines, I want to talk about the types of simulations Plasticomp can help you with. Of course, we do a mold flow simulation just to see how the part's filling out. We also do a fiber orientation simulation to make sure that you're getting fibers in the right direction compared to your stress loads. And from a finite element stress analysis standpoint, we can run the stress analysis. We can run a displacement analysis after it's being loaded just to make sure you're not getting too much deflection. Then we can help you out with a warpage simulation just to make sure the part doesn't come out of the mold too warped. We also help out with renders, which is that center diagram. That can let your marketing team know if they're okay with how the part looks ahead of time. All right. If anyone has any questions, we'll start answering them now. Thank you.
Thank you. A few of you have already submitted some questions, so we're going to jump right in. If you'd like to submit a question, just type it into the question window on the side of your screen and hit the submit button. While we're answering your questions, we'd like to ask you to complete a feedback form, which is located on the bottom left of your screen. And question 1, does the long fiber does the LF go on surface?
Yeah, I think we can answer that one. I believe what they're asking is, can you see the long fiber on the surface of the parts? And the answer is, if the product has not been wet out properly, which means fully impregnated with the polymer in between all the filaments, you will get bundles of fiber on the surface, and that's typical of a product that has been more wire coated and has just a jacket of polymer around the fibers. With our process, we tend to fully impregnate the filaments so that we get a higher quality surface. Now, it's also important with processing, you have to have the proper temperatures, and mold temperature is of particular importance so that you'll get a nice looking aesthetic part and the fibers do not migrate to the surface. And those are, of course, things that we can advise on.
And what do you mean by fiber chemistry?
Just mean the sizing that is applied. So there's typically going to be chemicals that are applied to the fiber surface to help promote bonding between the polymer and the fibers themselves.
And are you able to, or how can you align the fiber in an injection molding?
So this is done by your gating selection and your geometry. So if you need fiber to be aligned in a certain section, you can start adding your gate in a way that promotes the fiber in that orientation, and you can control the thickness there. You can also use sweeps, fillets, and curves to kind of start aligning the fiber in the sections you need it to be. Now, it's going to be difficult to have full control over the fiber orientation all over your part. That's where it's key in the FEAs to find out where do you need your fiber orientation, so you can optimize your gating locations for that.
And what are some of the differences in runner size and gate size is there between the short and long fiber materials?
I think Mark Henry touched on that a little bit, that with the short fiber materials you can have smaller gates and runners that except are going to cause more shear in the process. We typically will go, in general, larger is preferred. So for example, on a runner system, we'd recommend a full round runner that's a 1/4 inch diameter. You can do trapezoidal designs that are 1 1/4 inch by the depth of the runner. And with gates, we like to be as large as practical as well, depending on the part size and the configuration of that part. We at a minimum would advise a 1/4 inch by 1/8 of an inch land length. So again, as large as practical is the best way to look at that. Anything to add, Mark Henry?
Yeah, as Eric said, it also depends on the part size and what the surface condition that is interfacing with that gate. Larger is better. It depends what you're okay with when it comes to the fiber breakdown too. If you have a smaller part, you can also have a smaller runner because you have a smaller flow length. So overall, you're getting less shear on the part. So that 1/4 inch was a good reference to think about.
Thank you. And is the MT grade an impact modified one?
Yeah, it does have some modifiers in there to help with that durability.
And is 12 millimeters typical for long fiber pellet length?
It is typical, however, it's dependent on the size of the machine you're running on. In general, 12 millimeters seems to fit best for feeding and maintaining fiber length, but we do have some customers that are molding on smaller machines, and it'll bridge up when feeding into the feed throat, so we will chop to a different length for them, maybe 6 millimeters, but 12 millimeters is very typical.
And what are the additional benefits of other molding processes like compression or injection compression to maintain the longer fiber length?
Yeah, you're going to definitely improve fiber length if you're doing compression or injection compression, because you are, again, going to be lowering your pressure overall and minimizing shear. So those are definitely good processes to look at. With compression molding, you can't get as detailed of a part, so that's one drawback. They're typically more of a 2D type structure.
Yeah, injection molding, one of the pros of that is it's a little bit simpler than compression molding. It's a lot more self-automated in a way than compression molding typically is. Compression molding is having huge strides right now for automation, which is great. But if the question also was along the lines of what does retaining that fiber length do for all those different processes, the way I like to think about it is rebar in a cement structure. The longer the length, the more interfacial bonding that's happening with your resin matrix. I hope that answers the question.
Okay. During analysis, do you use any material molding to accurately predict the material properties in the part?
Now, do you mean... So, let's say prototype molding, if that's the question that's being asked. Yeah, prototype molding can be done on this. There's going to be high shear rates on the mold, so you're not going to want to use a weaker material for that prototype mold. If that was the question. Eric, did you
Yeah, maybe you can
that?
repeat that. I'm sorry I missed that. I was looking at the incoming questions.
Sure, sorry about that. During analysis, do you use any material molding to accurately predict the material properties in the part?
Yeah, I think if I understand that, we're just looking at, can we confirm some of the properties by molding. We try to do that with our test bar molding, but I don't know if we're understanding that question. We may have to talk offline with the person that asked that.
Yeah, please send us an email and we can also talk to that question. But also, we do get a lot of experience on the abilities of the material, what the material is going to behave like from a lot of our past moldings, thickness variations in the past moldings. So we're able to test a lot of different thicknesses and different geometries based on past moldings. Typically, clients aren't looking to make a prototype mold or mold just for the sake of research on their part, because that adds cost to the situation. But yeah, we would be more than willing to do that if the client is willing to pay for that test mold.
Yeah, and I think to add on to that, we've got existing tools that, yeah, we can confirm some of our simulation results with.
Correct. Yeah.
Okay, and just this will be our last question. How much does the long fiber length break down during the remelt process of the pellets in the injection press screw?
So I'll let Eric speak to just the mold side of it, and I'll speak to how the design has an effect on that.
Yeah, it's dependent upon, the screw that's used, but if using the proper screw, which would be a low compression general purpose type screw, you can minimize the fiber length attrition in that area. There is some breakdown that occurs. What percentage, I couldn't answer. The majority of the breakdown is going to occur upon injection into the tool through the nozzle. That's where the majority of the stress is built up. Mm-hmm. But there's definitely some attrition that takes place within the screw upon melting.
Yeah, so the reason that's a tricky one to answer is there isn't a percentage in it. Now, it also depends on the injection speeds that you're using, and like Eric said, at the feed you're going to get your highest attrition rate. but also in the geometry of your part. If you're having a very long flow length, there's going to be more breakdown because you have higher injection speeds and you're pulling the material over a longer path. And also in your parts, you want to avoid the sharp corners, add fillets. As the fiber goes around a sharp corner, there's going to be more breakdown because there's more shear forces there.
Okay, and that concludes today's presentation. On behalf of Machine Design, I'd like to thank you for joining our webcast, and thank you to Plasticom for sponsoring today's event. And have a nice and productive remainder of your day.